Hey everyone, and welcome back to our channel. Ever wonder what magical transformations happen in your kitchen every time you cook? It's not magic, it's science. Today, we're diving deep into the fascinating world of food chemistry. And we're starting with something we all love, meat and other animal products. You know that incredible aroma when you sear a steak, or how a tough cut of meat becomes full off the bone tender after hours of slow cooking. That's all chemistry, my friends. We're going to uncover the secrets behind these everyday culinary miracles, from the sizzle in the pan to the flavor on your plate. Let's start with the undisputed star of the kitchen chemistry show, the Maillard reaction. Say it with me, Maillard. This isn't just simple browning. It's a complex chemical dance between amino acids, which are the building blocks of proteins, and reducing sugars. When you heat meat to around 300 degrees Fahrenheit, or 150 degrees Celsius, these two components react, creating hundreds of new aroma and flavor compounds. Think about searing a steak. That beautiful, dark brown crust. That's the Maillard reaction in action. It's what gives grilled chicken its savory taste, roasted turkey its golden skin, and bacon its irresistible, complex flavor. It's not burning, it's flavor creation at a molecular level. The key is high, dry heat. If there's too much water, the temperature won't get high enough for the reaction to kick off, which is why we pat our meat dry before searing. But what about the color change? When you buy a fresh piece of beef, it's usually a bright, cherry red color. This is thanks to a protein called myoglobin. Myoglobin's job in the muscle is to store oxygen. When it's bound to oxygen, it has that appealing red hue. As you cook the meat, the heat causes the myoglobin protein to change its shape or denature. This process forces the oxygen out and alters the way light reflects off it. The meat transforms from red to pink, and then to that familiar grayish-brown color of a well-done steak. So, the color of your steak is a direct visual indicator of how much the proteins have been cooked. Now, let's talk about texture. How does a tough, chewy piece of meat like a beef brisket or a pork shoulder become incredibly tender and juicy? The answer lies in another key component of meat, collagen. Collagen is a type of connective tissue, a tough, fibrous protein that holds the muscle fibers together. In cuts of meat that get a lot of exercise, there's a lot of collagen, which makes them tough. But collagen has a secret weakness: low and slow cooking. When you gently heat collagen in a moist environment for a long period of time, think braising, stewing, or slow roasting, something amazing happens. The tough collagen fibers melt and transform into rich, smooth gelatin. This gelatin coats the muscle fibers, making the meat feel moist, succulent, and incredibly tender. This is the science behind pulled pork, pot roast, and braised short ribs. It's the reason why patience in the kitchen is rewarded with melt-in-your-mouth results. Let's move from the stovetop to the mixing bowl and talk about eggs. Eggs are a culinary powerhouse, and their versatility is all thanks to their proteins. An egg white is about 90% water and 10% protein, primarily one called ovalbumin. In its raw state, these proteins are all tightly coiled up. But when you start whisking, you're introducing air and applying physical force. This causes the proteins to unfold, or denature. These long, unfolded protein strands then link up with each other, forming a network that traps the air bubbles you're whipping in. This is how you get a beautiful, stable foam for meringues or soufflés. If you add a little acid, like cream of tartar or lemon juice, it helps stabilize this network even more, giving you those perfect, stiff peaks. When you apply heat, it's a similar story. The heat denatures the proteins in both the yolk and the white, causing them to tangle up and solidify. This is what happens when you fry, scramble, or boil an egg. The liquid turns solid because the proteins have created a new, stable structure. It's a simple, everyday transformation that is pure chemistry. And what about dairy? Let's look at cheese. At its core, cheesemaking is the process of controlling the coagulation of a milk protein called casein. Milk is mostly water, but it also contains fats, sugars, and these amazing casein proteins, which are bundled in little spheres called mist. To make cheese, you add an enzyme, usually rennet, and a starter culture of bacteria. The bacteria consume the milk sugar, lactose, and produce lactic acid. This change in acidity causes the casein micelles to start falling apart and clumping together. The rennet then acts like a pair of molecular scissors, snipping off a part of the casein protein, which causes them to tangle up into a massive net. This net traps the milk's fat and water, forming a solid curd. The liquid left behind is the whey. The curd is then pressed, salted, and aged, developing complex flavors over time. Every type of cheese, from soft brie to hard cheddar, is just a different expression of this fundamental chemical process. Even making yogurt at home is a mini chemistry experiment. When you add a bacterial culture to warm milk, the bacteria get to work, fermenting the lactose into lactic acid. Just like in cheesemaking, this increase in acidity causes the casein proteins to denature and coagulate, but in a much gentler way. They form a delicate, fine mesh that traps the water, resulting in that thick, creamy, and tangy final product we know as yogurt. So you see, every time you sear a steak, whip egg whites, or even make yogurt, you're not just a cook, you're a practical chemist. You're manipulating proteins, fats, and sugars to create delicious new textures and flavors. Understanding the why behind these cooking techniques can empower you to be a more intuitive and confident cook. You'll know why you need to get your pan screaming hot for a good sear, or why a tough cut of meat needs time, not high heat, to become tender. It's truly amazing how much science is packed into our daily meals. Next time you're in the kitchen, take a moment to appreciate the incredible chemical reactions unfolding right before your eyes. Thanks so much for joining me on this culinary science adventure. If you found this interesting and want to learn more about the chemistry of cooking, make sure to hit that like button and subscribe to our channel. Don't forget to ring the bell so you won't miss our next video. Until next time, happy cooking. Hey everyone, and welcome back to our channel. Have you ever wondered what's actually happening when you throw a steak on a hot pan? You see that beautiful brown crust form. You smell that incredible aroma. Well, that's not just cooking, that's chemistry. And today, we're diving deep into the amazing chemical reactions that transform raw meat into a delicious meal. It's a journey from the farm to your fork, all explained by science. Let's start with the most famous reaction of all, the Maillard reaction. This is the holy grail of flavor. It's not just one reaction, but a whole cascade of complex chemical events that happen when amino acids, the building blocks of proteins, and reducing sugars get heated up. Think of it as a party where heat is the DJ. When the temperature hits around 300 degrees Fahrenheit, or 150 Celsius, these amino acids and sugars start dancing together, creating hundreds of new aroma and flavor compounds. That savory, roasted, slightly nutty flavor you love in a seared steak, a roasted chicken, or even the crust of bread. That's the Maillard reaction in all its glory. It's what gives food that irresistible golden brown color. Without it, your food would be a lot paler and, honestly, a lot more boring. But color isn't just about the Maillard reaction. Let's talk about why raw red meat is, well, red. It's all thanks to a protein called myoglobin. Myoglobin is found in muscle tissue, and its job is to store oxygen. When it's bound to oxygen, it has a bright, cherry red color, which we associate with fresh meat. But as you cook it, the heat causes the myoglobin to change its shape, a process called denaturation. As the protein structure changes, it loses its ability to bind oxygen, and its color shifts. It goes from red to pink, and then, as it cooks further, to a grayish-brown. So, the color of your steak is a direct indicator of how much the myoglobin has been denatured, which is why a rare steak is red inside and a well-done steak is brown all the way through. Texture is everything when it comes to meat. Raw meat can be tough and chewy, but cooking changes that completely. Here's the deal. Collagen is a tough protein that holds muscle fibers together, especially in cuts like beef shank or pork shoulder. If you cook these quickly, the collagen tightens and makes the meat even tougher. But when you go low and slow, like braising or stewing, something amazing happens. That collagen breaks down into gelatin, giving you tender, melt-in-your-mouth meat and a rich sauce. It's the secret behind those full-off-the-bone ribs and silky stews we all love. Heat changes proteins, but what about fat? It's super important for flavor and texture. When you cook meat, the solid fat melts, a process called rendering. This melted fat does some pretty cool stuff. It keeps the meat moist and tender by lubricating the muscle fibers. Ever had a dry, lean piece of meat? That's often due to not enough fat. Plus, fat carries flavor. Many tasty compounds from the cooking process dissolve in fat, spreading rich flavors throughout the meat. That's why a well-marbled steak is so loved for its juicy, delicious taste. Let's put it all together. Imagine you're searing a beautiful ribeye steak. You place it on a screaming hot cast iron skillet. The instant it hits the pan, the Maillard reaction kicks off on the surface, creating that deep brown crust and releasing those incredible savory aromas.